definition is the green shaded area, blue being where it's too cold, red being where it's too hot, and stars come in different temperatures and brightnesses, luminosities. So that distance, that habitable zone, is going to be different depending on the type of the star. Now, how are we finding planets? It's very, very simple. The technique we're using to find planets is very simple. We are not taking a telescope and tooling around the sky, taking pictures looking for planets. Okay? All the planets are detected indirectly by measuring the light from the parent star. And in this case, what we're doing is measuring the brightnesses of many stars simultaneously with very, very high precision, looking for the telltale dimmings of light that happen when a planet in its orbit about the star is aligned just right so that the planet passes directly between the telescope and the disk of the star itself, thereby blocking out some of the light. Okay? And that's depicted by the green cartoon, a plot which measures brightness as a function of time. And that dimming that you see is called a transit, when the planet transits in front. Okay? Simple. Not all stars are going to be geometrically aligned, so you have to observe lots of them. And in fact, for an Earth-Sun analog, the probability of having that alignment is like 0.5%. Okay, so you want to observe lots of stars. And you want to do it with very high precision. See, here's the thing. Here's a cartoon that shows a sun with a planet like Jupiter blocking out some of the light. That's a cinch. That's easy. We could do that from the ground. That amount of dimming is 1 part per 100, about a 1% dimming of light. No problem. Ground-based telescopes, in fact, we had a robotic telescope that we built up here at Lick Observatory, and the telescope was about that big around, the mirror. Very tiny, nothing fancy required. But we're not chasing Jupiters. We're looking for potentially habitable Earth-sized planets. That's the distinction. And here's what an Earth looks like. Put on your glasses. Can you see it? It's very tiny. Imagine the biggest hotel in San Francisco, downtown San Francisco, big 20-story building, and imagine every single room is occupied and the lights are on in every single room. And one person lowered their blinds by about 2 inches. That's the brightness change that we're trying to find. 1 part per 10,000. Okay? It's very tiny. So that means we've got to go out into space, because if starlight is streaming through an atmosphere, the Earth's atmosphere, you're going to have twinkling of stars, and the brightness is going to vary too much. Much, much more than this 1 part per 10,000. So we've got to have a space-based platform, and it has to be able to collect enough light to get the precision. And so here's the glass that's ground out for the mirror. That's the blank of the mirror. And you can see it's about 1 meter and something across. It's about 1.4 meters across is the mirror, in comparison with the Hubble Space Telescope, which was about 2 point something. So smaller than the Hubble, but of the same order of magnitude. That mirror collects the light and is going to send the light to a detector, right? We want to measure the brightnesses. And the detectors that we use are simply charge-coupled devices, which is the same exact thing that you have in your digital camera, except that our camera is about 1 square foot of silicon, and the one in your digital camera is about the size of your thumbnail, okay? It's the largest camera that NASA's ever launched into space. And it's depicted here. You can see there's the camera. It's got this gold metal thing that's just holding it in place as they lower it down. And you see this pattern of squares. Every square that you see is a module, and it's actually 2 CCDs that are sandwiched together. And there's an array of 21 of those modules. So that's the array that's actually measuring the light from the stars. And all of the light is being collected simultaneously, so you're taking brightness measurements of all of these stars at the same time. The spacecraft itself is about the size of a minivan, but it weighs about as much as a Volkswagen Bug. Interestingly, I love this picture because this is called Brutus. They took the spacecraft and they lowered it down into this big vacuum chamber that they could control not just the temperature of, but they could also control the frequencies of vibration to mimic what frequencies of vibration they would expect in space, so that you could map out or understand and calibrate what the instrument would do in that environment. And that was all done before launch. The spacecraft launched on March 6th of 2009. The week before we launched, there was a spacecraft that was launched out of Vandenberg Air Force Base that actually tanked in the Antarctic. That was really scary. The shell, you can see on the top here, there's this white part here. It's kind of like a clam shell, and that's what holds the spacecraft. The whole Kepler spacecraft is inside this top part. And just like a clamshell, it opens up, and it has a little mechanism to open it up. And the one the week before that launched, it didn't open. Changed all the orbital dynamics, and the thing dove right into the ocean. So NASA had to go through and compare the parts lists for both of these systems. And there were millions of parts, and they had to go through them one at a time and see all the, down to screws. Everything, wires, everything, to see what they had in common, to see what the risk was. And miraculously, it only delayed our launch by about 2 days. Anyway, it went off flawlessly. We put this very sensitive instrument on top of a tower of explosives, and we blasted it into space. And so the first thing we were